The stars are a mystery. And that mystery is what has inspired countless stories and ideas. From ancient religions to Star Wars. Our attraction to the canvas of light stretched across our night sky is ingrained in our psyche as a civilization. It inspires us. It allows us to dream of the possibilities, and motivates countless writers, artists, scientists, and engineers. Unfortunately, unlocking these mysteries has always been expensive, prohibitively expensive, and complicated, reserving the privilege to only a select few. I hope to improve that with the system I'm describing to you today. The system I'm describing, for the sake of clarity, I'm going to call it the slingshot. It is a system that, once in a low Earth orbit, will allow many small probes to be launched all at once. With this system, I hope to address the limitations of space exploration with a low-cost system that has the versatility of CubeSat, the deployability of Starlink, the simplicity of TARS, and the capability, to an extent, of breakthrough Starshot. I think of it as a version of spin launch, with all the benefits of accessibility, simplicity, and capability, but none of the complexity or dependence on imaginary technologies. The slingshot is a system that can be built today, with today's technology and today's materials. No science fiction required, just a creative application of science fact and insight into elegant engineering. The process of the slingshot is fairly simple. Launch a deployment system into low Earth orbit, spin it up with incredibly long tethers, and fling an absolute ton of probes at a particular target. You can imagine that where current space discovery and exploration technologies are akin to a sniper rifle, this system is a shotgun. What I mean by that is that current probes and space systems need to be highly accurate to reach their targets, while also carrying their sensors and cameras. Besides the science, they need to correct for small errors in their initial deployment to get to where they need to go in order to conduct the science they are intended to conduct. That means carrying guidance systems, carrying propulsion systems, carrying communication systems, carrying fuel, and making sure all of that works, all of that complexity operates with 100% reliability. And that kind of reliability means cost. Cost and weight, cost and complexity, cost in testing, cost in materials, cost in development, and cost in deployment, with no guarantees that it will work when it gets to where you want it to be. It is an all your eggs in one basket philosophy, and that is never a good approach to accomplishing any kind of goal. However, due to the cost mentioned earlier, it has been necessary. The following video illustrates, through animation, a paper I'm submitting that describes the math and engineering of the slingshot. But instead of showing math and formulas, which can be confusing to many people and misrepresent the simplicity of this concept, I made this video to help people understand just how simple the idea is. As someone who has had to teach myself engineering, math, and science to a very great extent, I've come to realize that most of these heady disciplines can be understood without the need for college degrees or fancy and expensive college classes. And even though my paper is written in the language of math and engineering, it is describing something even a child can understand. And like many things inspired in space, it begins with a rocket.
15 seconds. T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff.
Vehicles pitching downrange.
MOD chamber pressures are nominal.
Power and telemetry nominal.
MECO.
Stage separation confirmed.
I'm back. Start up.
Here, the slingshot is orienting itself with onboard reaction wheels. It is preparing itself to be at the optimal angle for the next step. Notice all the clear cylinders clustered around the main body of the satellite. Those are the probes. Each one is small, simple, and tough. By having many probes launched all at once, there is a huge saving in cost. But it is not the only benefit of this system. Let's see what happens next. Now we see the slingshot spinning up using ion thrusters. In order to get to other planets in our solar system, the slingshot only needs to spin up to about 76 RPM. 76 RPM is very slow, but we will see that rotational speed is not what is required to go fast. We can imagine that the slingshot is still spinning at 76 RPM. But for this step, let's stop the motion and understand what is happening. Here we see just one of the probes attached to one of the release wheels. The slingshot consists of many of these wheels and probes, repeating itself hundreds of times around the main body of the satellite. And as you can see, it is no more complicated than a fishing line and weight. As a matter of fact, for the anglers in the audience, wrapped around that wheel is a Kevlar cord. The cord wrapped around the wheel can be purchased off the shelf from deep-sea fishing supply stores. There is no exotic engineering here. Recall that this system is spinning. So as we let out the cord, as we allow that probe to unreel from the release wheel, from the spool, centripetal force is going to pull that probe out exactly like you would think. But here's the trick of it. That probe is going to be let out until it is a kilometer long. It is going to be almost a half a mile from the main body of the satellite. Now, recall as well, there are 100 of these wheels around the main body of the satellite. As each of these cords are let out, two things need to happen. One, there needs to be a counterweight let out at the same time, on the opposite side of the satellite. That counterweight is going to be a dummy weight. It is only going to make sure that the system stays in balance as it spins. Second thing is that the satellite will need to add more energy into rotation as the arms are extended. It will need to add energy as the probes are extended to keep the RPM to where it needs to be. Just like how an ice skater, when they extend their arms, they slow down. At this step, the slingshot is extending its arms, and extending them a lot. Where an ice skater is extending its arm only a couple of feet, the slingshot is extending its arms almost a half a mile. So those ion thrusters will need to kick back on and keep firing as the cord is let out in order to keep the speed up and keep those cords nice and straight. Now we can imagine that the probes are fully extended to their full 1 kilometer length. Since I showed earlier 3 layers of wheels wrapped around the main body of the slingshot, we would have 3 layers of probes at each position when fully extended. Here's the trick of it though. When these probes are fully extended, each one of them, at 76 RPM, will be experiencing over 6,000 Gs. That is a massive amount of force. But this is also where all the energy is going to come from to launch these probes at escape velocities. This force, 6,000 Gs or more if you want the probes to go faster, is going to create a significant design constraint on how the probes will need to be designed. As an example, the probe will need to be completely solid. No air gaps, no moving parts. Completely solid state. Even a battery with the layers of electrolytes and metals will likely deform to the point of non-functionality when exposed to more than 6,000 Gs. So power, sensors, and any communication technology on board will need to be all solid state. Fortunately, with today's technology, this can be achieved relatively inexpensively. Camera sensors, electronics, data storage, these are all in solid state these days. And if you were to encase these electronics in a solid medium like epoxy, they can be held stable at a very low cost. The only thing that will be a real challenge would be power. You can imagine embedding solar panels in these probes, but at this size, and assuming that you want these probes to go far from Earth, that would be too little power for even a cell phone camera. The only solution I can imagine for power that would have a chance of surviving these forces would be an RTG, a radioisotope thermal generator, the same technology that we used for the Voyager probes. These can be made very small, but they are not cheap. So until solid-state batteries are made available, and at the capacities to last years on end, the power system would be the largest cost to this design. And now we have release. This step is critical. Since the probes have no onboard propulsion or means to correct any error in trajectory, the release timing needs to be absolutely precise. Any error at this step will be amplified as the probe travels for millions of miles toward far-off targets. That said, the design of this system allows for some error in this step. Although you want to be as accurate as possible, as I mentioned earlier, the slingshot is a shotgun, not a rifle. The idea is that you send a lot of small, simple probes with the expectation that most of them will not make it. Either due to system failure, errors in targeting, or damage due to the challenges of space travel, we can expect many of these probes will not survive to do the science they were designed for. So we do what most organisms do in cases like this. Have lots and lots of babies, knowing that most of them will not survive. We send out lots and lots of probes, knowing that most of them will not make it. And in a similar way to organisms, the probes do not need to be identical. Some may be set up to pick up the visual spectrum, others may be configured for infrared, others for magnetic fields. This further increases the value of this approach because if the infrared probe fails, you still have the visual probe capable of, at least, some science being accomplished. By releasing a lot of probes, with a lot of different configurations, we increase the likelihood of success significantly while keeping the costs and complexity to a minimum. As well, there is nothing to say that all the probes need to be released at once. You can send many probes to different targets at the same time, or at different times, just by changing what probes are released. This adds to the flexibility of the slingshot by allowing several targets to be studied with one rocket launch. Flying by large planetary bodies has the capability of both altering trajectory and velocity. In this case, flying by Mars causes the probes to spread out, each group of probes moving to different targets or orbits. And here we are flying by Jupiter, using its immense gravity to send the probes into a long orbit, intercepting with Io as they are captured by Jupiter's gravity well. Finally, we have Pluto and the bodies beyond into the Kuiper Belt. One of the limitations of the Horizons probe that visited Pluto very recently was that it got only one chance to image Pluto. Imagine if you could send volley after volley of small probes toward Pluto. How much more insight and science would we be able to accomplish? In this case, only one set of probes managed to make it to Pluto, but another set was following soon after, prepared to capture the other side of this dwarf planet, all based on when the probe was initially released.
Slingshot is not a new idea. There are rarely new ideas in the field of astrophysics and astronomy. The stars inspire imagination and curiosity, and have done so for thousands of years. Every idea that can be imagined has probably been explored in some sense or another, whether it is based in today's science or tomorrow's. This is merely an approach that solves a lot of the problems associated with accomplishing those ideas. And like all things space, it starts with a rocket.